Section 1.4 talks about different common classes of graphs. And in the warm-up, you looked at the classes of graphs that we'll call cycle graphs and path graphs. So let's start with a few definitions. We say in a graph G that a circuit is just a closed trail of length 3 or more. All right, so let's remember what this means here. Closed means it starts and it ends in the same vertex. And a trail means it's a special type of a walk where potentially you're allowed to repeat vertices, but you cannot repeat any edges. Right, so a circuit might be something like this. Right, A, B, C, D, E. So a circuit might be something like A, B, C, D, E, C, A. Right, you repeat the vertex C, but you don't repeat any edges, and you start and you end at the same vertex, and there's at least length 3. Right, so a circuit would not be something like A to B to A. Right, A, B, A is not a circuit because the length of it is only 2. Okay, now a cycle is a special type of a circuit. It's a circuit that has no repeated vertices except the first and the last one. So up here, this is not a cycle because it repeats the vertex C in the center here. But you could have, for example, in this graph, you could have the cycle A, B, C, A, or you could have the cycle D, E, C, D. Right? There's various different cycles here. And so a K cycle is just a cycle that has length K. So these are examples of 3 cycles. Now we also talked about earlier in the class, we talked about a complete graph of order n, which we denote Kn. And it's just a simple graph, so no loops or no multiple edges. So it's a simple graph of order n, so n vertices, such that every pair of vertices in the graph is adjacent. Right, so K4 would be a graph with 4 vertices, and every possible pair of edges is adjacent, so we need to connect this to all the other vertices, and connect this to all the other vertices, and then this, and that's it. Right? So K4 has 1, 2, 3, 4, 5, 6 edges, so the size of this would be 6. K5, a complete graph on 5 vertices, is going to look like this. Right? It has, let's see, it has 5 vertices, and if we counted up all the edges, it would have 10 edges, size 10. And so if we wanted to try to determine the size of Kn in general, Kn is just a vertex with n distinct vertices, right, 1 through n, all possible edges between them. The size is just the number of edges, so how are we going to count that? Well, one way to do it would be to use choose notation from combinatorics or from probability. You might be familiar with this. There's n vertices to choose from, and we need to choose 2 of them to form an edge. In other words, all the 2 element subsets of the vertices is going to account for an edge. So there's n choose 2 many vertices. Maybe we know that this is n times n minus 1 divided by 2. Another way to think about this is by saying, well, every vertex in the graph is connected to exactly n minus 1 other vertices. It's connected to every vertex except itself, right? So there's n minus 1 edges coming out of 1. There's n minus 1 edges coming out of 2, all the way around. So it's sort of like n minus 1 times n, right? N minus 1 edges for each of these n vertices, except that's going to double count every edge in the graph because each edge is going to be counted twice, once for its first endpoint and once for its other endpoint. So we divide by 2. Okay, so there's different sort of ways to try to justify why the size of this would be n choose 2, but that's n times n minus 1 over 2. All right, so that's another sort of common class of graphs, the complete graph. We say an empty graph of order n is just a graph that has n vertices but doesn't have any edges at all. And so the size of an empty graph of order n is always going to be 0. An empty graph has no edges, so its size is 0. And an easy exercise would be to prove that the complement of the Kn graph is the empty graph of order n. Remember, complement just means if you take out all the edges that are in Kn and replace them with any edges that aren't in Kn, you'll end up with the empty graph. Okay, it's a good exercise to make sure you understand the definition. But another common class of graphs are bipartite graphs. So we say that G is a bipartite graph if you can partition the vertices of G into two distinct sets, U and V, such that every edge of your graph has to join a vertex in U to a vertex in W. Right? In other words, you have your graph and you can sort of split it up into two different parts. Right? Here's the vertices of U, here's the vertices of W, and any edge in your graph has to be connecting a vertex in U to a vertex in W. Right? Maybe there's lots of connections here, maybe they're not all there. Right? But in particular, there's not going to be any edges connecting a U vertex to another U vertex. And there's not going to be any edges connecting a V vertex to another V vertex. That's what it means to be bipartite. It means you can sort of break up the vertex set into this way so that every edge is connecting a U vertex to a W vertex. And we call those sets U and W our partite sets. So as an example, or a couple of examples, each one of these graphs are bipartite. And if we want to think about what our partite sets would be, well, in this first case, we can sort of see the way that it's drawn. The vertices up here are all connected to vertices down here. And there's no edges connecting, let's say, X to Y, right, or Z to S, or Z to R, or S to R. So our partite sets here would be the set X and Y, and the set Z, S, R. All right. Now this one is harder to see the way that it's drawn here, but we can break this up into partite sets. Here's our partite set, let's call it U, and then here's our partite set W. Right, so U would be the set containing M and K, W would be the set containing J and L, and you can confirm that the only edges in this graph are connecting a vertex in U to a vertex in W. All right, and now finally, this last example here, this one's definitely harder to see. How are we going to split this up? Well, it makes sense to sort of start somewhere. Like, I'm going to start with B, because B has a lot of edges coming out of it. If I put B in the first partite set, U, that means that A needs to be in another partite set. Right? And E needs to be in another partite set, and C needs to be in another partite set, right? Because there's edges connecting B to A, B to E, and B to C, which means they have to be in different partite sets. All right, so now let's think, where should D go? Well, D is connected to C and to E, which means it can't be in this set W, so we'll put D in the first set. And similarly, F is adjacent to E, so I can't put it in the set W, so I'll put it in this first set here. And we can check and make sure that there's no edges connecting B to D to F. There's no edges adjacent between A, E, and C. All right, so it might make sense to try to redraw this graph with B, D, and F up here, A, E, and C down here. And then we can see that there's no edges connecting these guys and none connecting these guys. We just have an edge, let's say, here, these three edges. We've got D is connected to E and C, and we've got F is connected to just E. Right, so when we draw it like this, it's a little bit easier to see that it's a bipartite graph. Now, a good question to ask is every path graph bipartite? Is Pn a bipartite graph for all n? Is a cycle graph always going to be bipartite? Right, so this example here is C4. This was a bipartite graph, but is every cycle graph going to be bipartite? This is a good thing to think through and try and convince yourself one way or the other. Okay, couple more definitions. We can extend this idea of bipartite into, let's say, tripartite, right? Three-partite or four-partite, by saying that a graph is k-partite if the vertices can be partitioned into k disjoint sets, where every edge is going to be connecting vertices from different partite sets. And if every pair of vertices chosen from different partite sets is adjacent in the graph, then we call it a complete k-partite graph. Right, so for example, we would say k sub nml represents the complete three-partite graph, where the first partite set has n vertices, the second partite set has m vertices, and the third partite set has l vertices. So just to make sure everyone understands what this means here, let's maybe do an example try to use some colors to make it a little bit clearer. If we wanted to draw the graph K1, 2, 2, it means you've got one vertex in your first partite set. I'll just color that with purple. We've got two vertices in our second partite set. I'll color those with green. And then we have two vertices in our third partite set. And the complete part is just saying you have every possible edge connecting two vertices of different colors, right? So no red to red vertices, no green to green vertices, but every other pair needs to be connected, right? So this purple vertex, let me use a different color here. This purple vertex needs to be adjacent to every non-purple vertex. So we have these vertices here. These green vertices need to be adjacent to every non-green vertex. So here, here, and here. And then similarly here, here, and here. And then that's it. The reds are already connected to the greens and the purples. All right, so we would call this K1, 2, 2 because it's a complete three-partite set where the cardinalities of the different partite sets are 1, 2, and 2. Similarly, if I wanted to draw the graph K1, 1, 2, well, I'd have a partite set of size 1, I'd have a partite set of size 1 again, and then I'd have a partite set of size 2. And I'm going to have to connect every pair of vertices that has a different color here. So purple's going to get adjacent to every non-purple vertex, green is adjacent to every non-green vertex, and red is adjacent to every non-red vertex. So the only vertex, or the only edge I'm missing here is this one connecting the two reds. And finally, K3, 3, the complete bipartite graph that has 3 vertices in the first partite set and 3 vertices in the second partite set. And the K part means I have to connect every possible edge between a purple vertex and a red vertex. So that means I need these 3 edges here, I need these 3 edges here, and I need these 3 edges here. Okay. So a good sort of thing to think through is how many edges are you going to have in general in some kind of a complete K-partite graph, and how many vertices are you going to have? But another thing that we can prove, and we'll go over this in class, you can read through it in the notes as well. This is theorem 1.4.1. We can prove that a non-trivial graph G is going to be bipartite if and only if it contains no odd cycles, right? Which sort of makes sense. If we look at this K3, 3 graph, this doesn't even necessarily have to be complete, but this one is. If we wanted to find a cycle, that means it's a circuit that doesn't repeat any vertices. So for example, you could have this cycle here, something like this, right? That would be an odd cycle. Or wait, that would be a cycle, but it would be even length, right? 1, 2, 3, 4. So we're sort of always bouncing around purple to red to purple to red, and you can maybe see why it's going to end up being only even circles, but it's a good thing to try to think through if you have time before class.